In this video, we're going to see how we can do lane detection, which is used for self-driving cars. It's a simple lane detection application, not using machine learning or AI, a simple lane detection using image manipulation from OpenCV functions. So it will give a good hands-on experience on using some of the OpenCV libraries, but at the same time give us an introduction into lane detection. Now, we are not using AI or machine learning, and there is no way training going on the lane detection. So if you're thinking about this on a production level, this library or this function will not work out. However, for anyone who is getting into lane detection or starting lane detection or working on self-driving cars, this will be a very good introductory application. So let me go into the command prompt and see and just give you a quick demo of how this function is going to be looking like. So I have this window open up here and it gives out the result. So you can see the lanes are being detected by the OpenCV, and it draws these red color lines on it showing the lanes, the displays of the lanes. Now this function will work out if the lane are in a straight line, but if the lanes are converging or diverging or they're rotating, and if they're curved, this is not going to work out. It's only going to work if it is a straight line. Now with that being said, we'll go into the code and see how it runs. I'm going to comment everything for now, and we comment everything to the point of this, and I will slowly open up each commit and each application, each function, and each line of this Python application and show you what it is doing. So the first thing we want to do is import the OpenCV library, where we are going to be using all the application, all the advanced image manipulation applications. The next is the NumPy, and NumPy we are using mostly for matrix manipulation, a little bit of matrix just to read the images. I'm not sure, it's nothing too crazy, just to read the images and give out the information of some arrays and matrices. That's about it. Most of the heavy lifting is going to be done by OpenCV. Now let's go down, all the way down, and this over here, if you see the OpenCV wait key function, release and destroy. These are almost an essential part of an OpenCV Python application. Wait key is something which you need in order to show. You run this imShow function, which we'll see later, and if you have an imShow function, you got to have wait key. Without wait key, imShow function cannot run. The next step, once everything is done, once your application is completed, done, you want to release the cap, and capture is nothing but the variable that is going to hold your video. Now it could be a video file, it could be a webcam, it could be a live stream, whatever it is, but capture is what it is holding on, and you want to release before you are closing your application. Once you're done with that, you're destroying all the windows that OpenCV might have created, and this also exits the program. So we'll now start writing running the application one by one step at a time. So the first step in this Python application, once you take care of all the importing of the libraries and everything, the first step is to read the video file, and the video file is test1 mp4, and I have this folder here, the lane detection folder, and you can see the lane detection Python file and the test1 mp4. Both of them are in the same folder. Hence, I'm able to simply write test1.mp4, and this is how it's also uploaded on the GitHub code, which is in the description below, and I don't need to provide. But if you were to put the video in a different folder or a different directory, you want to provide the directory file name or path name, and we are storing that capture into this cap variable. Once you have defined that, you want to start reading the frames from the video, and video is nothing but a sequence of images, placed one after the other, and that's a video. So now you want to start reading the images. So you're using this while loop, and this while is going to be reading the images as long as capture is still open and it's still supplying the images from our test1 video, and you're using cap.read in order to read the frames, the images from that video, and saving it into this variable called frame. And this is the original, this is the main image from that video, where you can see it's a road and a car which is driving on the road, and that frame is being saved here. The first image manipulation we're going to be doing is canny image, and you're going to do canny edge detection. And canny edge detection is a very old edge detection algorithm, and it allows to read the image and detect edges in it. So we'll see how it works, and we'll come back to the top of the application, and we will uncomment this portion, which is the canny edge detection function. And you can see it takes the argument image, and it comes down and it sees whether the image, if there is an image or not. If the image is not there, then it releases the capture, it destroys all the windows, and it exits the program. So this is just a flag to see whether the video is still running or not. You may or may not need this, but just to be, not to create any more errors in the program. So once this check is done, now it goes into starting to manipulate the image. The first step is to convert our colored image from BGR to gray. And you're using this convert color function of OpenCV. You're providing the original image and you're converting the BGR to gray. OpenCV saves colored images in the BGR format, unlike the RGB format, which we normally know, and many of the machine learning applications use RGB, but OpenCV uses BGR. You're converting BGR to gray, and that is what canny edge detection needs. And you're saving the gray image into this gray variable. You're now defining a kernel size of 5. And what is this kernel? You are going to first blur the image before passing into the canny edge detection. And you're doing blurring in order to reduce the noise level in the images. Because if the image is crisp and sharpened and you're going to be running an edge detection on that, it will bring up a lot of noise that you're not interested in. So you're going to be providing this kernel image, and this kernel has a size of 5 by 5. So any image or any object in the image which is less than 5 by 5 will simply be erased by this Gaussian blur. And once that noise is removed, that initial level of noise is removed, you're going to do a canny edge detection on this. And this canny edge detection is going to be done on this gray image, and it saves into this canny variable, and it simply returns the canny file, this image, back to our main function. So let's go back and go down and see. So we have this canny image shown. Now let's see how this image looks like. We'll write cv2 im show canny image, comma canny image. So let's save this and come back to our command prompt and run this. So you can see that it's detecting all the edges in the images, and it's detecting every image. It's detecting the trees, the cars, the roads, the side, everything is being shown, and it's too much of information we are not interested in. We are only interested in these two things. So let's see how we can take care of that. Go back to our code, and we are going to let the function know, the program know, that we are not interested in all the edges present in the image. We are only interested in the location where the lanes are. And by human knowledge, we know that the lane is going to be present on the lower half of the image, because that's where the road is present. So we are going to simply crop that much region and then do our algorithm search on it. So let's uncomment this, and this is going to be done by region of interest. So we're going to be creating a region of interest in our canny image. So let's go up and see where the region of interest is and what it does. So the region of interest function takes the canny image, it takes the image, it obtains the height. The height is given by the shape variable of the canny image, and the zeroth element of the array gives the height, the second element gives the width, and there is also a third element which gives the channel size, but in our case we are only interested in the height and the width. We are also creating a mask because that's what we are interested in. We want to remove everything else except the lane on the road. The third step is to create a triangle, and we'll see why we are creating that triangle, but just to see what the triangle looks like. So the triangle has these coordinates. It takes in 3 coordinates. We're using NumPy for this, and we are giving 3 different coordinates of the triangle. So basically the 3 points of the triangle: the 200 by height, 800 by 350, 1200 by height. So these are the 3 points of the triangle. So I'll show you what this triangle is basically going to help us make look like. This fill poly is making basically masking out everything else except that portion which is being defined by this triangle. And once we are done with that mask, we just do bitwise AND so that we can remove the external feature and only keep that much region which is needed for which is being defined in that triangle and where the lanes are supposedly going to be present. Once we do all that, we just return the masked image. So let's go down and see what this triangle has done for us. So we will, instead of calling the CV2IM show here, we will call it in this. And let's bring it back to our format, and we will now run cropped canny. Instead of the canny image, we'll do cropped canny because we are interested in to see how the triangle is affecting our program. So let's run this, and you can see that it is only running that region. You can, I'm not sure if it's visible, but there is a triangle coming up here whose tip is here and the 2 edges are here, and it's removed everything else and only kept the points which are interested to us. Let's come back here. Now once we know where the lanes are present and once we have done the lane detection, it's only a matter of identifying the lines present in that image and then drawing the lines on it. So these are 3 or 4 functions that we're going to be using in order to do that. So first is hook lines, and hook lines is a algorithm, hook line transform. It's an algorithm which is supposedly supposed to run on a canny edge detection, and it gives an approximate presence of lines in an image. We're going to be using hook lines and average lines to obtain the location of these lines. Once these 2 lines are detected, then we go and display these lines on the image. So let's go back and see what hook lines does for us. Not sure how exactly it is pronounced, but hook lines is an algorithm. It's a very neat algorithm. If anyone is interested, leave a comment and I'll make a video of what hook line does and how it works. It's a very neat algorithm, and there's something interesting going on what they have done in order to detect lines in an image. So this is the function, and OpenCV has that function already. So you're using hook lines and you're just passing the cropped image and defining where the lines are. So you're just returning the lines, but those lines are not, they're just a probability of where the lines are, so they're not strong. So you want to once you're done with hook lines, you do average slope intercept. So this is where the average slope intercept does, and it takes those images, those lines, and tries to obtain the exact slope of that intercept, so it can identify the exact location of the lines. So out of all the lines that are present, it's only interested in the lines that may represent a lane, and that is what we're going to be doing in this function. So it's a pretty much function out here which is going to be using the slope, and we're using another function called make points, and it goes through the lines and it goes through each line one by one, and it tries to identify which line is important and which line is not. and you after that you find the slope of these lines, and you're using this make points function, which is out here, and it uses the slope of these lines, and we are defining the slope of this line based on the image sizes. The image size is given by here, the y1, y2, x1, x2. These are nothing but the image size, and based on that we are defining that the line should be so and so big. So in this case we're giving it that it should be 3 by 5, the intercept. So these are basically the ways that you are assuming your lines are going to be. Now again, these are our assumptions. If you were to give a different image or a different scenario or a different video file altogether, then you would have to change these functions accordingly. So these are some of the things that you would want to change. And even in the case of the triangle, this is the triangle that worked out for this particular video file. If you're running on a different video file, then you would want to change the coordinates based on where your lines are. And I would say even the added weight function will also need it. So once we are done with detecting the lines, once we have known where all the lines are, we go into the next line, which is the display lines function. And we'll say display lines. Display lines is nothing but a simple OpenCV function of drawing lines on an image, and you're using the image where you want to draw the lines, but you're also using the lines that we detected in the original in the previous function with the slopes that we've obtained. And you're just using a line image. This is a blank image that we're using, and if there is no lines, then there should be it should not draw anything. But if there is a line, then it draws a line, and you're drawing it on the line image, and you're drawing it on the coordinate x1 y1 and x2 y2. This is the coordinate of the line, and the line is represented by the starting point and the ending point. This is the color of the line, and this is the thickness of the line. So BGR, so it's B is which is blue is 0, G which is green is 0, R which is red is 255, and that is why you see a red colored line, and you're just returning the line image. Once you have done with returning the line image, you are going to add some weight, and the reason we are doing that is because the line which we are drawing, it is on top of the image, and you want to give some weight to that line. So you come back here and you uncomment this function, and so that you're providing some weight to the image, so that the line is visible. You're basically adding these two images. The line image is the image that we created in the initial function from the previous function, sorry. And this line image is just drawn on a black colored image which we had created here using the zeros like, and this line image is being created on that black colored image, and we are now adding this line image with our frame image, the original colored image. So we are just adding these two, but we're using this add weighted so that we give some weight to the line image as well, so that it's not fully merged and it's not visible at all. So we give some sort of weight, and this is a type of a merging or addition of two images, a function being in OpenCV. Once we have done with all that, we go back and we return the image into this combo image, and we simply display. We can uncomment this guy and save this and go back and run our code. So this should show how it was earlier in the demo, and you can see how the lanes are being detected. Assumedly there used to be a lane here previously, that's the reason it's causing some error initially, but now when there is no image, though no lanes present, then it's safely detecting the lanes on the road. So you can see how this function works on a straight path. Now since you're using hook line transform, and hook line transform is only able to detect straight lines, hence this function will only work on straight paths. But if we were to run on curved roads or roads which don't have full perfect lines or lanes, then this algorithm will unfortunately not work. But now we know how lane detection is runs and how we can use it for self-driving cars. It's a good starting point, and we'll see in the future how we can develop this algorithm further. If you like this video, leave a comment and subscribe to the channel. And if you like this journey, if you like such programs, such technical challenges, leave a comment and I would be happy to run into them. Until then, take care. Bye bye.